Hello, my name is Walker Hale, and this is my Physics 2211 Lab 1 report for constant velocity. So starting off with the table of contents, we'll start with the introduction to the lab, then move on to Newton's second law of motion and explaining that. Then we're going into the analysis of the canteen's motion, the computational model of motion, the comparison between the two, the what if, and the sources of error. Starting with the introduction, the purpose of this lab is to apply Newton's fundamental laws of motion in real life. This lab in particular focuses on Newton's second law of motion being the momentum principle with the constant velocity. It focuses on this law by comparing two position time graphs created by both collecting real-world data and using a computational model. For Newton's second law and explaining that, Newton's second law explains how forces acting upon a system from its surroundings can cause changes in that system over time. And for this, if no net force is present in the system, this can change a momentum being zero, resulting in a constant velocity. And one other major part about Newton's second law is the equation of force equals mass times acceleration seen in the top right. And by deriving this equation, we can get two ones that we will be using today, being the momentum update formula, which is the change in momentum equals the mass times the change in velocity, as well as the velocity update formula, which is seen at the bottom as well. Moving on to the procedure of the lab, we will start by recording the motion of what I chose to use as a canteen, a video of a canteen, moving in a straight line at a constant speed. We'll then send the video into the tracker software to track the canteen's position at several time intervals. We'll utilize the starter code and glow script to create a computational model of the canteen's motion, create position versus time graphs for both datasets, and then compare both the results with a singular graph. With the analysis of the canteen's motion, there are a couple assumptions that need to be made first. For this lab, both air resistance and friction were assumed negligible. The normal force is equal to the directional force, and only the x-axis displacement will be observed in this lab. The position of the canteen is tracked as soon as it enters the camera's field of view, and the first data point taken of the canteen is the assumed origin of the graph for this lab, as seen at the bottom. And the canteen is moving at a relatively constant velocity throughout the video and experiment. So the initial position starts at the origin being 0, and then the initial velocity is 0.07 meters per second at the first time interval being 0.033 seconds, which would also hopefully be the constant velocity throughout. In terms of our computational model in GlowScript, the mass of the ball does not affect its velocity as it will be canceled out in the formula. Delta t will be set to 0.033 due to the frame rate of the video, as one data point is selected per frame. And this position and velocity update formulas will be used, circled in red, as to map out the position of the ball in the data set. So you can also see that the vector is 0.02, which is also due to the frame rate. Looking at the comparison of the graphs, we can actually see that they are quite similar. As you see, the tracker is in blue, as well as the computational is in red. They both have an upward trend, and they start at different positions, but then as you see throughout the graph, they get more and more similar to be quite similar graph. Now, finally, we have our what if and what does it means. And for these, we have what if the positive and negative x were changed on the axis, and how many pushes or pulls were added together to give zero net force in the case you observed. Starting off with question 1, if the axes were flipped, then the slope of the graph would be downward rather than upward. This is due to the object moving in the negative direction rather than the positive, due to the position on the right being negative rather than it being positive. This would also result in a negative velocity as well due to this negative position change. And for the second question, it is not possible to exactly pinpoint how many pushes or pulls at play to give zero net force. In this experiment, the canteen is being pushed to achieve a constant velocity, but there is no way to truly achieve this naturally without accelerating due to external forces such as friction, which is why we cannot create a constant velocity, and the tracker graph is overestimating the position over time. Now finally, for our sources of error, I found 3, being human errors, computing errors, and surrounding forces. With human errors, we have that you could have pushed the canteen too hard, which would lead to a variable velocity rather than constant. There's computing errors, being programming errors in GlowScript possibly, incorrect tracker inputs, or wrong calibrations. And then finally, with surrounding forces, the role of friction and air resistance are present when the rolling of the canteen occurred, and were not accounted for and assumed negligible.